about how to draw tangents to a circle and all those things? No, right?
No.
So we just basically started circles and we saw like what is the center and radius of this circle, right?
Yeah.
Minus g comma minus f is the center, and the radius is basically root over g square plus f square minus c. And this happens because you will complete the square and you will write it as x plus g whole square plus y plus f whole square is equal to this side you will bring minus c and you will add a g square and f square. So it will come this, right?
Yeah.
And because of this, this sort of becomes like a distance formula, distance from minus g point and minus f point.
What is C?
C is any constant.
Okay.
C is any constant. It can be any number. Just like G and F are constant, C is also a constant. So
Okay.
you remember, right, that we saw a 2-degree equation. This was our 2-degree equation, and this equation could be multiple things. This equation could represent a pair of straight lines, and it could represent a circle. It could be many things, right?
Yeah.
When we did pair of straight lines here, everything, all of these were numbers, like constants, b, g, f, c. So it's the same c. It's just that for a circle, you need to have a is equal to b, and you need to have h is equal to 0. If that is true in this equation, what you end up getting is something like this: ax square plus ay square plus 2gx plus 2fy plus c is equal to 0. And you can divide by a throughout and get this equation. Plus c by a is equal to 0. This is what we get from the general 2-degree equation, and we can write it. The standard circle equation is written by assuming that this quantity is called 2 capital G, this quantity is called 2 capital F, and this quantity is called C. And in that case, your equation looks like this. And then you can say that the center of this circle will be minus G minus F, and the radius of this circle will be root over G square plus F square minus C, right?
Okay. Yeah.
You understand all this, right?
Yeah.
Okay. So what we learn today is, first of all, things like distance of a line, distance of a line uh, from a circle, not distance actually, intersection of a line and a circle, intersection of a line and a circle, and from there we can derive the conditions for tangent. So line and a circle. So let's think about a random circle like this, and let's say this is a circle which is center as at 0 0, radius is a. So the equation of this circle would be x minus 0 whole square plus y minus 0 whole square is equal to a square, right?
Yeah.
The equation of the circle is x square plus y square is equal to a square. Let's say we have a random line y is equal to mx plus c, a line in plane, somewhere it will be. It line could be like this, it could be like this, or it could be tangent, right?
Yeah.
There are basically these three possibilities. You can have no intersection, you can have two intersections here, two intersections, and you can have touches the circle, right?
Yeah.
So if suppose you were asked to find out what is the point where, or what are the points where the line cuts the circle, right? So in coordinate geometry, the meaning that we assign to intersection is basically that you have one equation, you have another equation. If you want to find out the intersection, you just solve those two equations. Whatever is a common value of x and y is a point that will lie on both of those equations, right?
Yeah.
Just like in straight lines, we have two equations, we solve them to find this point, right? So right now we have a circle equation and a line equation. And if we solve these two together to find say x and y, then those points will lie both on the circle as well as on the line, right?
Yeah.
So that is what we will do. So our approach is basically solving it. So x square plus y square is equal to a square, and let's say y is equal to mx plus c. So I can take this value and put it in this equation. What I will get is x square plus mx plus c whole square is equal to a square. So it will become x square 1 plus m square plus 2mcx plus c square minus a square is equal to 0, right?
Hmm.
This is my equation that is coming. So now this is a quadratic equation in x, quadratic in x. So technically it should have two roots for x, right?
Yeah.
It can have two roots of x, it can have zero roots for x, or it can have only one repeated root. Like these are the three possibilities for any quadratic, right?
Yes.
Depending on whether the discriminant is greater than 0, discriminant is less than 0, and discriminant is equal to 0, right?
Oh yeah.
Right.
Yeah.
So what we will say is that the line will cut the circle two times. If there are two distinct roots of x, then obviously the situation is something like this, where one x is here and one x is here, right?
Yeah.
So basically we can say that discriminant of this will be, discriminant is 4m square c square minus 4 times 1 plus m square into c square minus a square. And simplifying this a little bit, you will get 4m square c square minus 4 c square minus a square plus m square c square minus a square m square. And now simplifying it further, we get this will cancel this, and we get plus 4a square minus 4c square minus plus 4a square m square, right?
Yes.
So this discriminant, if this discriminant was greater than 0, what we have is a intersection at two different points, right?
Yeah.
So now, if you think about it, uh, you can cancel 4 from everything here in this inequality. And what you get is a square into 1 plus m square is greater than c square, right?
Yeah.
Okay. So this tells us that if this condition is satisfied, we have two intersections. If discriminant was
Wait.
hmm,
Why do you cancel out all of the terms in like the very third step, like 4a square minus 4c square plus 4? Oh, you divided the 4. I thought you canceled out the terms. Never mind. Sorry.
I'm canceling 4.
Yeah. Okay.
If
Okay.
d is equal to 0, then we have the condition for tangent, right?
Yeah.
Tangent would happen when d is equal to 0. So that would mean that there is only one root and it is a repeated root here.
Yeah.
So d is equal to 0 will be when a square 1 plus m square will be equal to c square. So what you will get is c should be plus minus a root over 1 plus m square, right?
Yeah.
For it to be a tangent. So now you can say that if I have a circle x square plus y square is equal to a square, then if y is equal to mx plus c is tangent to the circle, then c must be equal to plus minus a root over 1 plus m square, right?
Yeah.
So your equation of the tangent becomes y is equal to mx plus minus a root over 1 plus m square. So that is a convenient equation because now we know the equation of the line in terms of the slope of the line and the radius of the circle, right?
Yeah.
there is only two unknowns here, m and a. And m and a are basically, one is slope of the line and one is radius of the circle, right?
Yeah.
And this also tells us two things. There are actually two tangents that are possible, right? Two tangents are possible, and because there are two equations here, y is equal to mx plus a root over 1 plus m square, and y is equal to mx minus a root over 1 plus m square, right?
Yeah.
And notice that both of these lines are parallel because their slopes are equal, right?
Yeah.
So the tangents will be somewhat like this. One tangent will be like this, one tangent will be like this. Obviously, they should be parallel to each other, right?
Yeah.
So at a given, if you are given a slope, you can try to find the tangent to the circle with that particular slope. Okay.
Yeah. Can you
Okay.
just hold on a minute? I'm just need to write it all down.
Yeah. Yeah.
Okay, I'm finished.
Okay. So what we have is the condition that y is equal to mx plus minus a root over 1 plus m square is tangent to the circle x square plus y square is equal to a square. Now, this actually came because we said discriminant was equal to 0 in the quadratic, right?
Yeah.
And the condition from there had come c square is equal to a square into 1 plus m square. That is how we wrote c as plus minus this thing, right?
Right.
Now, there is another way to interpret it, which is quite easy to understand. So, like, you don't have to solve the quadratic to get this. There's another way to get this, which is this one. So let's say we have a circle like this. Center is 0, comma 0, radius is a, and let's say I want to make a line that is tangent, right?
Yeah.
So I know one property, that if this y is equal to mx plus c line is tangent, then it will be perpendicular to the radius at this point, right?
And we can use point to line.
Huh? What?
We can use point to line for that.
We can use point to line distance, right?
Yeah.
So what we can say is, from 0, comma 0 center, if I drop a perpendicular on the line, right? That will
Mm-hmm.
give me distance from center to that line, right?
Yes.
And that distance, according to the formula, is mod of 0 minus m into 0 minus c by root over 1 plus m square, right? Why? Because
Yeah.
the equation of the line is y is equal to minus mx minus c is equal to 0. And to find distance from any point to this line, you have to put the point in it, right? And divide
Yeah.
by the root of the coefficient of x and y squares, right? Sum.
Yeah.
So this distance is coming out to be mod of minus c by root over 1 plus m square. Or minus 1 mod can be taken as 1. So it is mod c by root over 1 plus m square. So
Right.
mod c by root over 1 plus m square is the distance. Now, obviously, it is commonsensical to say that if the circle touches the line, then obviously this distance should be equal to radius a, right?
Yes.
If distance is greater than a, then no intersection is possible, right?
Yeah.
And if distance is less than a, then it will cut two times, right?
Yeah.
Two intersections, correct?
Yes.
So distance is equal to this is equal to A is the tangent condition. And notice that that is the same condition. If you square it, it's the same thing here. See,
Yeah.
c square by 1 plus m square is equal to a square is the same as this statement. So an easy way to get the condition for tangent, a line to be tangent, is to just take the perpendicular distance from the center to that line, right? And check
Yeah.
whether it is bigger than the radius or smaller than the radius or equal to the radius, right?
Yes.
Okay. So all this is fine. All this does what? It tells us that if we have a circle and we want to find a tangent with a particular slope m, right? Like
Yeah.
the question can be asked that find the tangent with slope half. Find the tangent with slope m is equal to half to the circle x square plus y square is equal to 3, right? Then
Yeah.
what we'll do is, okay, I know the radius of the circle A is equal to root 3 and I know m is given. So y is equal to mx plus c. So half into x plus c, and c should be equal to mod plus minus a root over 1 plus m square, right?
Yeah.
So c should be plus minus root 3 root over 1 plus m square is 1 by 4. So you get 5 by 4. So you get root 3 into root 5 by 2, right?
Yeah.
So you're getting the equation y is equal to x by 2 plus minus root over 15 by 2, right? These are the two possible tangents with this slope, right?
Yeah.
However, sometimes questions are slightly different and you can be asked a question where find the tangent to the circle x square plus y square is equal to a square at a point x1 comma y1 on the circle, basically, right?
Yeah.
So instead of giving a slope here, what they have given you is a point on the curve, right?
Yeah.
And now you have to find the equation of the circle, equation of the tangent. So let's say this is my circle and this is my point. This is x1 comma y1. So I have to find the equation of a line like this, right?
Yeah.
Correct. Now equation of circle is known, x square plus y square is equal to a square. I have to find equation of tangent. Tangent is what, right? So
Yes.
the first thing that we know is that let's assume tangent equation is y is equal to mx plus c. No, wait, maybe not. This is not the first thing. The first thing you can say is that x1, y1 should lie on the circle, right?
Yeah.
So you can say x1 square plus y1 square should be equal to a square, right?
Yeah. Yes.
Okay. Then the next thing that we know is center of this is 0 comma 0, right?
Yes.
So we know the slope of this, right?
Yeah.
Slope of this particular segment, right? 0 comma 0 to x1 comma y1 is y1 by x1, right?
Yes.
So slope of the tangent will be what? Minus x1 by y1. Why? Because tangent has to be perpendicular to this line, no?
Yes.
Is it making sense?
Mhm.
So slope of tangent is coming out to be minus x1 by y1, right? So we have m tangent is equal to minus x1 by y1, and we know that tangent passes through x1 comma y1, right?
Yeah.
So we know one point and the slope also. So we can find the equation of the tangent now. Equation of the tangent will be y minus y1 point slope form. So passing through y1 comma x1 is equal to m tangent, which is minus x1 by y1 multiplied by x minus x1, right?
This is point slope form.
Yeah. So the point is x1 y1, the slope is this, right?
Yeah.
So now just multiply throughout by y1, you get y1 minus y1 square is equal to minus xx1 plus x1 square, right?
Yeah.
And the equation becomes xx1 plus y1 is equal to x1 square plus y1 square, right?
Yes.
But that is equal to a square, right?
Yep.
So this is your final equation of the tangent. And this is very convenient, notice. At a point x1, y1 on the circle this, the tangent is x1 plus y1 is equal to a square, right?
Yeah.
So why is this an equation of a line? Because this is a single degree equation in x and y. And this is a 2-degree equation, so this is a curve, right?
Yeah.
So the way in which we found it is important, and you should make a note of this. Like, what was the first condition? We said that x1, y1 lies on the circle, right? So we have this relation. The second condition was we found the slope of the line joining the center to the point where we need the tangent, right?
Yeah.
That slope was y1 by x1. So therefore, slope of tangent has to be minus x1 by y1, correct?
Yeah.
And once you know slope of the tangent, you also know a point through which the tangent passes, which is x1 comma y1. Therefore, we can write y minus y1 is equal to this point slope form.
Yes.
At the end, we get an equation x1 plus y1 is equal to x1 square plus y1 square. And then we realize that x1 square plus y1 square is equal to a square. So the equation can be simplified and written like this, right?
Yeah.
The same method will also work in a more general situation. Like, suppose I gave you a circle like this, 2gx plus 2fy plus c is equal to 0. This is a circle, and you have to find tangent to this circle at x1 comma y1, right? So try to do this. So think about it. The same idea, nothing new in the idea, just slightly more complicated example, right?
Yes.
Try to do this. Think about it. Equation of the tangent we need. So the approach is the same. you have to realize that the circle center is something else, right?
Yeah, well, so the equation we have for the circle is in general form where the center is negative g and negative f.
Hmm.
And so the tangent would be, and so the slope would be x, no, y1
Hmm.
plus f over x1 plus g.
Y1 plus f over x1 plus g is the slope of this line.
Right.
So slope
And
of
so,
tangent.
and so basically we need to do -1 divided by.
Hmm. So that will come out to be this.
Yeah.
Now we just know that okay, point is x1, y1, and slope is this, right?
Yeah.
So point slope form. So y minus y1 is equal to negative of x1 plus g by y1 plus f multiplied by x minus x1, right?
Yes.
So we will simplify it a little bit because we'll see a pattern. So once we simplify, we'll realize. So multiply both sides. So it becomes y1 minus y1 square plus fy minus fy1 is equal to negative of x1 minus x1 square plus gx minus gx1, right?
Uh, yes.
We get y1 minus y1 square plus fy minus fy1. Bring this side plus xx1 plus x1 square, no, plus xx1 minus x1 square my plus gx minus gx1, right, is equal to 0, right?
Yeah.
So we will write it in a slightly better way, xx1 plus y1. Now after that we have noticed that there is a gx and there is a uh, one second, have I made some mistake here? Plus gx1, is it a plus? Have I made a mistake in multiply? No. Okay, fine. I'll just write gx. Okay, and I'll write plus fy. I don't think I made a mistake in multiplying. So this is what is coming. This and this. And then I have minus x1 square minus y1 square minus fy1 minus gx1 is equal to 0, right?
Yeah.
This term, this term, no, this term, all the terms are taken care of. Yeah.
Yeah.
Yeah. So this is my equation that is coming right now. Now, one thing that we will realize here is that x1 comma y1 lies on the circle, right? x1 comma y1 is a point on the circle, correct?
Correct.
So therefore, x1 comma y1 will satisfy the circle equation, no? So you have x1 square plus y1 square plus 2gx1 plus 2fy1 plus c is equal to 0, right?
Yes.
Right.
Yes.
Then we can say this is minus x1 square plus y1 square plus fy1 plus gx1 is equal to 0. Now we can say that this is gx1 square plus y1 square plus gx1 plus fy1 is equal to minus gx1 minus fy1 minus c, right? From here,
Yeah.
like I have basically split my 2gx1 as 1gx1 here and 1gx1 on the other side, right?
Okay. Yeah.
So I'm just writing these four terms here because these four terms are coming here, right?
Yeah.
So then I will, instead of this, I will write this. So what I will get is x1 plus y1 plus gx plus fy. And then there is a minus of this minus, right? So it will become a plus gx1 plus fy1 plus c is equal to 0, right?
Yeah.
So now notice that the equation of the tangent that we are getting after a little bit of simplification and putting this from here, what we get at the end is this equation. this equation x1 plus y1 plus, you can take g common and say x plus x1, right?
Yes, but in it says that this whole part like x1 plus y1 plus gx plus fy minus x1 squared minus y1 squared minus fy1 minus gx1 is equal to negative x1 squared plus y1 squared plus fy plus gx1.
Where? Here, you're saying.
Yeah.
This was equal to 0, no? This was the equation, right?
Yes.
I'm just saying take negative common here in all these terms. They become positive like this, right?
Oh yeah. Okay.
And then I'm saying because x1, y1 lies on the circle, we have this equation also,
Yes.
plus 2gx1 and stuff, right?
Yeah.
So that positive quantity, these four terms, this positive quantity can be written as minus gx1 minus fy1 minus c, right?
Oh yeah. And then you took like this part of the equation and
And
then like
put this, I'm
yeah.
putting this here, right?
Yeah.
So
Okay. Got it.
that will become plus plus plus, right?
Okay. Yeah.
And then I'm taking g common and I'm writing it like this, right?
Yes.
The reason we are doing all of these manipulations is because now there will be an almost magical result. Like we right now know that the circle is the equation is this, tangent is this, right? At x1, y1, right?
Yeah.
Now, before this, we had already proved that if the circle was x square plus y square is equal to a square, right? Then
Yes.
then the tangent was coming out to be x1 plus y1 is equal to a square, right?
Yes. Yes.
In the previous derivation, we showed that for the circle this at point P x1 y1, the tangent equation will be x1 plus y1 is equal to a square, right? And
Yeah.
here circle was looking like this. Again, at point x1 y1, the tangent was this. So can you notice some pattern here? Every time what is happening is at x1 y1, if you're taking a tangent, you're doing something to the circle equation, right?
Yes.
So see, x square is becoming x1, right? Y
Yeah.
square is becoming y1, right?
Yeah.
And notice that c constant was unchanged, right?
Yes.
And here also see, x square is becoming x1, y square is becoming y1, and this was actually, this can be written as a c constant in this side, right? Minus a square. The equation of the tangent is this, where the constant has not been touched, right?
Yes.
So basically, three things you are seeing which are happening in both the circle and tangent pairs, right? Where
Yeah.
you are replacing what? X square with x1, y square with y1. You are saying c is same as c, right? And what happened to 2g, right? Or 2gx, right? What happened to that? 2gx became g into x plus x1. So basically, you're saying 2x became x plus x1, right? Correct.
Correct.
So x became x plus x1 by 2, right? And y became y plus y1 by 2, right? Correct. Like
Correct.
if you put x as x plus x1 by 2, you'll get this, no, from here, replacing.
Yeah, that makes sense.
So this is what is happening. And this is always true, like in the sense that anytime you need a tangent equation, if you know the point where you need the tangent, right, you can just directly replace.
Okay.
So for example, let's take an arbitrary circle equation, x square plus y square minus 4x plus 6y plus, okay, wait, the problem with the arbitrary equation is I will not be able to get a proper point on it. So x minus 2, one second, let me just draw it geometrically and then I will show you how it works. So let's say circle is centered at 2, 3, okay?
Yep.
So we will make a figure, circle of center 2, 3. This is 2 units here and 3 units here. Okay. So this is 2, 3 and radius 1. So obviously there will be some points on the circle that we can find, right? So one point on the circle would be what? If you go horizontally like this, it will be 3, 3, right? Right?
Yep.
So what I'm saying is circle is center is 2, 3, radius is 1, right?
Yep.
Radius is 1. So a point on the circle will be 3, 3. P 3, 3. This is our x1, y1. Okay. Fine.
Yep.
And,
Yeah, that's true.
and circle equation will be, I will just write the circle equation now. So I will write it here. Minus 4x minus 6y you should do, right? Then only the center will be 2, 3, right? Plus constant. Constant should be such that radius is equal to root over g square plus f square minus c, right?
Yep.
The c constant is, I don't know. I'll make the constant now because radius is 1 is known. So 1 is equal to root over g square plus f square. G square plus f square will be 4 plus 9, right? Minus
Yep.
c. So you should have 1 is equal to root 13 minus c. So c should be 12, right?
Yes.
So the equation of the circle is x square plus y square minus 4x minus 6y plus 12 is equal to 0, correct?
Yes.
Now, I will first get the tangent by the method that I have just told you. And then we will check whether it makes sense or not, right? So the method that we have just seen is replace x square with x1, y square with y1, x with x plus x1 by 2, y with y plus y1 by 2, and c is constant, right?
Yes.
Okay. And x1, y1, the point here was 3, 3. So x square should be replaced with what? 3 into x, right? Y
Yes.
square should be replaced with 3y. X should be replaced with x plus 3 by 2. Y should be replaced with y plus 3 by 2, right? And c should be
Yes.
3, right? So if I do this replacement in this equation, let's see what comes. 3x plus 3y minus 4 times x. So 2 times x plus 3, right? Minus 6 times y. 6 times y plus 3 by 2, right? Here I have cancelled the 4 by 2, 2, right? Plus 12 is equal to 0.
Yes.
So you get 3x plus 3y minus 2x minus 6 minus 3y and minus 9 plus 12 is equal to 0, right? So notice
Yep.
y gets cancelled and it becomes 3x minus 2x x minus 6 minus 15 minus 15 plus 12. So x minus 3 is equal to 0, right? X is equal to 3 is my line. X is equal to 3 is the vertical line like this. And notice that it makes sense that this line is tangent because this was a horizontal radius, right? From 2,
Yes.
3 to 3, 3, this line was just line y is equal to 3, right? And obviously the line x is equal to 3 is tangent to the line y is equal to 3 at this point. It's perpendicular to it, right?
Yes.
Are you understanding that you are getting the correct tangent equation?
Yeah, I'm understanding.
So in general, what I will tell you is that if you have a curve like this, right? In
Yep.
general, it could be anything. It could be a parabola or an ellipse or a hyperbola or a circle. If you have a curve like this, if you need a tangent to this curve, tangent to this curve at a particular point, at a particular point. What is that point? X1 comma y1. X1 comma y1, right?
Yes.
The standard trick to get the equation of the tangent is this. Replace x square with x x1, y square with y y1, x with x plus x1 by 2, y with y plus y1 by 2, and xy with x1y plus xy1 by 2, and c is remaining constant, right? If you do these changes, if you do this transformation on the equation of the curve, the resulting equation is the equation of the tangent at this point. Okay.
Okay, yes.
In case of a circle, we didn't have this term, right? In case
Yeah.
of a circle, this term was not there, so it was slightly easier. Only these things were there, right? And this thing, this
Yeah.
rule is valid for circle, ellipse, hyperbola, parabola, anything basically that has a 2-degree curve, right? And the reason it works, we have already proven that it works for a circle. Okay, we found the tangent by normal methods earlier, right? At x1, y1.
Yeah.
We found the tangent equation by a regular method by doing slope and stuff, point slope form. But now
Yeah.
we are saying that we don't need to do all that, just directly write the answer. This is the equation of the tangent. I'll just say g into 2x will become x plus x1 plus 2y will become y plus y1 plus c is equal to 0.
Yeah.
So directly write the answer. So it saves a lot of time and effort if you know the point where the tangent is supposed to be found, right?
Yeah.
The actual explanation or the actual proof of this for a general 2-degree curve, it requires a little bit of calculus. So right now we will not do it because actually you will need to show the slope and stuff and find the equation and prove it, right? But
Yeah.
we don't need to know the proof right now because we know in specific cases how we got it. We see that it is working for circles. It will also work for parabolas and stuff. We'll see that. Okay.
Yeah.
So remember this rule. This rule is there in SL Loni on page number. Let me tell you one second. Page number 109, 119 and 120. So article 151. Okay.
Let-
Article 151, page 119, 120. So you can check that it is there, and that should help you find the equation of the circle. Now, after this point, there is nothing much. Sometimes people also ask you to find equation of the normal. Like if you know the tangent equation, equation of the normal is pretty straightforward. Basically, the meaning of normal is any line that is perpendicular to the tangent, right?
Yeah.
So if your tangent is at x1 comma y1, basically your normal to a circle will pass through the center, right?
Yes.
Because then a line perpendicular to tangent actually passes through the center in case of a circle, right? So
Yeah.
equation of normal will be very straightforward because it is, suppose the circle was a simple circle at the center is 0. So your point is 0, 0, and this point is x1, y1. Equation of normal is y minus y1 is equal to m, and m of this line was actually just y1 by x1, right?
Yeah.
Y1 by x1 into x minus x1, right? So your equation becomes x1y minus x1y1 is equal to xy1 minus x1y1. And this can be written as xy1 minus x1y, and this cancels, is equal to 0, right? Basically.
Yeah.
Yeah, actually, we didn't need to do all of this because this is a line from the origin, right? So y is equal to mx is the equation, right?
Yep.
Which is the same thing as this. In case the circle center is not at the origin, you will have to do a little more work, but still it is fairly straightforward. You just have to write that it passes through x1, y1 and has slope, whatever we know, right?
Yes.
So normal is a line perpendicular to the tangent. And if you know the tangent equation, you can always find the normal equation. It's not a big deal. So that is important. Then one thing that now we will look at is, which is not directly like relevant in your coordinate type of questions, but we will look at it anyway because it is a powerful idea, which is the idea of power of a point. Okay. Power of a
Yep.
point and common tangents. We'll see these two things. So power of a point and common tangents to two circles. Common tangents. So These two things will finish the circles chapter. So power of a point with respect to a circle. Okay. So far, what we have done is we have taken the circle equation and written the circle equation in terms of your Cartesian coordinates, right? Correct.
Yes.
Now
Yeah.
what we will do is we will just try to convert the circle equation into polar coordinates. And polar coordinates, I think we had briefly touched upon that any point x comma y can be written in a different way by noting its distance r and angle theta, right?
Yes.
So x comma y is a location of the point in the coordinates. Now instead of that, you can say it is r cos theta comma r sin theta, right?
Yes.
That is also the same location, correct?
Yes.
So polar coordinates basically says that instead of xy, we will use the symbols r theta, where r is distance of the point from the origin, and theta is the angle that the line which joins it to the origin makes with the positive x-axis. Angle with positive x, right?
Yes.
Okay, so basically any point in space you can write using r theta form. It's just equally good representation as x comma y. Now what we will do is try to get the equation of a circle in this r theta form. Okay, so let's say this is my origin. Let's say this is the center C, right? Correct.
Yes. Yes.
Now we have some point on the circle here P, and radius of the circle is, let's call it A. Okay, A is
Yeah.
the radius. Okay, now I don't want to write C and P in terms of x and y. I want to write them in terms of r and theta. Okay, so what I will do is I will join this C to the origin, right?
Yeah. Yes.
I will say that this OC length, let's call it capital R, right? OC.
Yes.
O is this. Let's call OC capital R, and let's say our angle, this angle with the x-axis, this angle, let's say, is alpha, right?
Yes.
Now, I will also join this P to the O, OP. Let's call the OP length as small r, right?
Yes.
Correct. And let's call this angle as theta, okay? So P
Yeah.
is the point r small r theta, C is the point capital R alpha, right?
Correct.
Correct. And now what we will do is we will join this, and we know the length here is A, right? Radius, correct?
Yes. Correct.
Now look at triangle OPC. In the OPC triangle, we actually know the length of OP is given by small r, the length of OC is given by capital R, and we know the length of PC is equal to small a, right?
Yeah.
Correct. We also know
Yes.
that angle POC is equal to theta minus alpha, right?
Yes. Theta.
Correct.
Max. Yeah. Correct.
So now in triangle OPC, if I do cosine rule for this angle, I can say cos of theta minus alpha should be equal to this square plus this square minus this square. So capital R square plus small r square minus a square by 2 capital R small r, right?
Yeah.
Correct, no? So
Yes.
now what we'll get is we'll just simplify this equation a little bit, and we'll say r square plus capital R square minus a square minus 2r cos theta minus alpha is equal to 0, right? So
Yeah.
we'll say r square minus 2r cos theta minus alpha into r plus r square minus a square is equal to 0, right?
Yeah.
Now this equation is an equation where the variables are small r and small theta, right?
Yes.
Because actually the center of the circle and the radius of the circle were given to us, right?
Yeah.
Capital R is known, alpha is known, A is known, because then only you are being asked to find the equation of the circle, right?
Yes.
And this P point was the unknown point lying on the circle, which should always satisfy some equation, right? Just like if I had drawn this same thing in Cartesian coordinates, I would have said P is my arbitrary xy, and always distance of xy from the center's position will be equal to A, right? Correct?
Correct.
And that's why you used to get the equation x square plus y square is equal to A square. X and y stood for a random point on the circle, right?
Yes.
Just like that, instead of x and y, we have r theta, and r and theta stands for a variable point on the circle, and other things are known, right?
What does WRT at the? I mean, what does the R theta mean?
What is the r theta mean? That is
Yes,
the
like this thing.
polar coordinate for P, no?
Polar. Oh yeah, polar corner. Okay. Sorry, I was confused. I didn't hear you properly.
I mean, that is the whole thing that we are doing. We are not doing Cartesian x and y. Instead of that, you are doing r and theta, right?
Yeah.
I mean, if you don't know what that means, then nothing is making sense, no? Then r theta polar coordinates, it means this is distance r and this is angle theta.
Yeah. Okay.
And center is r alpha, which means distance is capital R. This distance is capital R, and its angle is alpha, right?
Yes.
And this was small r and capital theta. And after that, we joined this triangle and we did cosine rule to get an equation, right?
Yes.
Now, this cosine rule, what I'm telling you is this equation is an equation with two variables, small r and theta, which stand for a random point on the circle, right? P.
Yes.
Right? Just like in this equation of a circle, the Cartesian equation, x and y stand for a random point on the circle, right? X
Yeah.
comma y, right? So we say that x comma y satisfies the circle equation, then it lies on the circle. Similarly, we'll say that r theta, if they satisfy this equation, it lies on the circle, right?
Yes.
So basically, this is the polar equation of a circle at an arbitrary point. Center is given, radius is given, theta and alpha are given, and A is given. Then this is the equation of the circle, right? But
Yes.
not in the normal form, the polar form. You don't need to remember this. I'm just showing you this in order to prove something. Now, what I'll say is look at this equation. Let's say this is a quadratic equation in R. So obviously it should have two roots for small r, right?
Yes.
Two roots for small r, basically r1 and let's say r2. What does it mean to have two roots for small r? What you need to understand here is that the line, this line, could intersect the circle at 2 points, right?
Yeah.
So you'll get 1 point P and 1 point Q. And what two roots means is 2 points will satisfy the circle equation while having the same theta, right? Like
Yes.
basically r1 comma theta and r2 comma theta both should satisfy the circle, right?
Correct.
This is r2 comma theta. What the difference between them is just that this distance is r1 and this distance is r2, right?
Yes.
So basically what we get is, okay, our two roots are r1 and r2, and those are points lying on the circle P and Q, right? Now,
Yeah.
one thing we can say for sure is that r1, r2 product of the roots in this equation is what? C by A, right?
Yes.
This product of the roots, right?
Correct.
Now, notice one thing. Sum of the roots was actually 2r cos theta minus alpha, right? By A, which is 1, right?
Yeah.
So sum of the roots depends on theta, no?
Yes.
But product of the roots does not depend on theta, right?
Yes.
Actually, what was known in the question, R and alpha and A are known already, right? Capital R, alpha and A are known, right? So
Yeah.
here 2R is known, alpha is known, but theta is unknown, right? Theta can change
Yes.
because the line could have been drawn like this also, no? Same, so, right? Many different thetas are possible, no?
Yes.
And they will still intersect the circle and you will still get 2 points, but the theta will be different, right?
Yeah.
So
Yes.
what will be different? Some of the roots will be different, but product of the roots is going to be fixed, right?
Yeah. It won't change.
It won't change with the position of the line or the nature slope of the line, right?
Yes.
And product of the roots is always going to be equal to capital R square minus A square, right? Correct.
Yes.
So what
Yep.
we are
Correct.
getting here is that if there is a circle like this, if I take a point like this, right? And
Yes.
I draw a random line like this, I can say that this is R1 and this much is R2, right?
Yeah.
And I can say that this distance is called capital R, right?
Yeah.
And radius of the circle was A, right?
Yeah.
I have just proved that R1, R2 will always be equal to capital R square minus A square, right?
Yes.
R1 into R2, the distance product of the roots is always this, regardless of how I draw my line, right?
Yep.
Even if I change the angle of the line, still product of the roots here R3 and R4 will be same, right?
Yeah.
So this product of the roots is actually what? It is the distance PQ multiplied by PR, right?
Yes.
So PQ into PR is equal to R square minus A square is called power of point P with respect to circle, with respect to circle. Here, basically what it means is this point is, as long as you fix the point, the product of lengths of two secant lines, like product of the intercepts made by two secant lines, right, is
Yeah.
always fixed, right? This into this, right? No matter
Yeah.
how you draw the line, your line could have been passing through the center also, or anyway, it could even be tangent. In the case of a tangent, your Q and R are coinciding, right?
Yes.
So if you call this P, you have PQ into PR is actually equal to R1 into R2 is actually just RR, right? It is PT square, right?
Yep.
And PT square is equal to, you're getting capital R square minus A square, right?
Yep. Yes.
Which confirms your Pythagoras theorem also, because this distance square should be equal to capital R square minus A square, right?
Yes.
Because it is 90 here, right? So
Yeah.
basically, for any point outside the circle, power of a point, power of P will be equal to R square minus A square, which basically means distance of that point to the circle center minus radius of the circle square, right?
Yeah.
That is very important, because what you will see is if point P lies on the circle, power is zero. Power is zero. Because if you lie on the circle, obviously R square is same as A square, right? Correct?
Yes.
And if point P is outside the circle, power of the point will be equal to, will be greater than zero. R square will be greater than A square, right?
Yes.
And if it is inside the circle, R square will be less than A square, so power will be negative, right?
Yeah. Yeah.
And what is power of a point? Power of a point is length of PQ multiplied by PR, right? And regardless of how you draw the lines, always this product will be same, right?
Yes.
So what we will see right now, you will not see immediately applications of this, but as we do slightly higher level type of problems, you'll realize that this power of a point can be used in many ways in Olympiad geometry questions. So it's a very important principle. Right now, we have just started doing the basics of it. If you have a point P, you have PQ into PR will be equal to PS into PT. PQ into PR will be equal to PS into PT will be equal to PC square minus radius square, right? This is the statement.
Yep.
This is the center, and radius is, let's say, R. Correct?
Yes.
If you change your point, if you change P and write it Q, then obviously it is not necessary that power of point P will be equal to power of point Q, right? Because you have changed
Yes.
everything. So
Yes.
that is your power of a point. Then the next thing that I want to discuss is common tangents to two circles, because sometimes at lower levels this is the kind of question that you might see. So you have one circle like this and one more circle like this, right? And
Yes.
let's say centers are C1 and C2 and radiuses are R1 and R2. Now I want you to tell me how many different possibilities are there for number of common tangents. Common tangents are tangents like this, which are tangents to both, right?
Yes.
How many possibilities are there for number of common tangents to two circles? Number of common tangents to two circles. And what are the conditions under which there will be that many common tangents? So I will give you the first couple of cases. So if C1, C2, the distance between the centers, right, is
Yeah.
greater than R1 plus R2, right?
Yeah.
Then four common tangents are possible. Why? Because I can draw two tangents like this. These are called direct tangents, and two tangents like this. These are called transverse tangents. Okay, this figure is not right, but you understand what I mean, right?
Yeah.
So there are two tangents which can be drawn like this, and two tangents which can be drawn like this, top top and top, bottom bottom, and they can cross, two of them. These the crossing ones are called transverse tangents, and the direct ones, these are called direct tangents. So in this case, the condition is if C1 and C2 is bigger than R1 plus R2, basically the tangent, the circles are separated apart, right? In that case, we have a possibility for four common tangents, right?
Yeah.
Now, if it was like this, for example, the circles were like this, right?
Yeah.
Actually, before that, I want to do another case. If it was like this, right? Here, there is a possibility of three tangents, right?
Yeah.
Correct? One tangent here also, if the circles were touching, right?
Yes.
So in this case, the condition that you would write is C1, C2 is equal to R1 plus R2, right?
Yes.
Correct. So if C1, C2 is greater than R1 plus R2, the possibilities are four tangents common. And here there are three common tangents, right?
Yes.
Now, the other case would be if they intersect like this, then only two are possible, right?
Yeah.
And that would be C1, C2 is less than R1 plus R2. Then only two common tangents are possible, right? Correct.
Yeah. Yes.
Another
Correct.
case is like this, right? If C1, C2 is equal to R1 minus R2, then one common tangent is possible, because here you see that R1 is this, R2 is this, C1, C2 is the difference, right?
Yeah.
Then there is only one possibility, right? Correct, no?
Yes.
And finally, last case is when one circle is completely inside another, then there is zero tangents. C1, C2 is less than mod of R1 minus R2, right?
Yeah.
And there are zero common tangents, correct?
Yes.
So what I want you to figure out is if there are two circles like this, and we have the situation that four common tangents are possible, right? How will you find the equation of the direct common tangent? And how will you find the equation of the transverse common tangent? Transverse tangent is this one, direct tangent is the top one. Okay. The I want to find equation of line L and equation of line M. Okay. And what is the information given to me? Circle C1, C2, radius is also given, center is also given. Okay. So think about this
Yes.
problem. We want to find out the common tangents to both the circles and both the types of common tangents. Fine.
Yep. Okay. Got it.
Try to do it. We'll discuss in 5 minutes. Okay. So hello.
Yeah, I'm here.
Yeah. So the idea here is you have to think of similar triangles, because otherwise it is really difficult to find the equation. So if the centers are like this, and if my tangent is like this, let's draw one transverse tangent. Okay.
Yeah, yes.
So here like this. So I know that this is radius 2 and this is perpendicular, right?
Yes.
And I also know that this is perpendicular and this is radius 1, right? So let's join the
Yeah.
centers. Let's join the centers. So if I join the centers, the line is wrong, but if I join the centers, let's say that this point is P. Okay. So what
Yes.
you can see is that triangle, let's call it T1 and let's call it T2. Triangle PT1C1 and PT2C2 are similar. Why? Because 90 and vertically opposite, right?
Yeah, the similar. Yeah, makes sense.
They are similar, and the ratio of the sides is R1 and R2, right?
Right.
That is given to us, ratio of the sides, correct?
Correct.
So we know the similarity ratio between these two triangles. Therefore, if we know C1 and C2 position, we should be able to find this, right? Because these sides will also be in the ratio R1 is to R2, right?
Yeah. Okay. Yeah.
Correct. Because similar triangles. So you get PC1 by PC2 should be equal to R1 by R2. And that means that we can find by section formula the position of P, right? Section formula, correct?
Correct.
And if we know the position of P, we just need the equation of the line, right? So we just need the slope now, right?
Yeah.
Correct. So we know a point here. We can write a relation that a line, suppose we have found P. So we have x1, y1 here, right?
Yeah. Yes.
So we can write line equation through x1, y1 will be y minus y1 is equal to m into x minus x1. We have to find m, right?
Yes.
So in order to find m, what we will say is, okay, what should happen is the perpendicular distance from C1 to line, this one, line L, is equal to R1, right?
Yes.
And R1 we know, C1 we know, so we can put C1 into this and get an equation which will help us find M, right?
Yes.
You understand? With a real problem, with some numbers, you will get a sense of what is happening. So basically, the idea is that you have to realize that if I want to find this tangent, I need to utilize the fact that these triangles are similar, because that will give me the position of this point P, right?
Yes.
Which lies on the tangent. Once I know a point on the tangent, I know y1, I know x1, and then I only have to find m, right?
Yes.
And in order to find m, I can use the condition that point to line distance from center 1 to the line, this equation should be equal to r1, right? Or you could have done with r2 also, with center 2, right?
Yeah.
And that will give you an equation to find m, correct?
Yes.
So that will be my tangent equation, and this is a transverse common tangent. If I wanted to do a direct common tangent, right, it's the same
Yes.
principle again. However, this time the similarity is on the other side, like this. So you have a tangent that is direct, so it is like this. The line is wrong, like this roughly, and somewhere it will meet this. What is the meeting point? Where it meets the line joining the centers. So you can say like this, draw a line like this. It meets it here, right? So
Yes.
you can say that this is 90 and this is 90. So obviously this small triangle is similar to the big triangle, right?
Yeah.
Because same angle here for both the triangles, and radius here is r1, radius here is r2. So we know similarity ratio. Therefore, this distance, because we know this distance, we'll be able to find the position of this point, right? We know
Yes.
C1, we know C2, we know the ratio of the big side and the small side, right? So we should be able to find the point P again, right? Once we know the point P, again write the equation as y minus yp is equal to m into x minus xp. And this line is point to line distance from any of the centers from C1 slash C2 to this line will be equal to R1 slash R2, right? Correct.
Yep.
And that will give you the equation that will help you find M, right?
Yes. Yeah.
Basically slightly long, but in some problems you might encounter situations where you have to find some common tangent. So I just wanted to mention this. More or less the circle chapter is done. We are not doing everything in SLONI. We are only doing stuff that is probable that you might see in your exams. There's a lot more stuff, but we will not do more. Right now, we'll just ensure that you know how to write tangent equations, basic circle equations, tangent equations, power of a point we saw, right?
Yeah.
Tomorrow, if tomorrow we are doing a class, right?
We are.
You,
Okay.
you are,
Yeah. We must be there.
I mean, we can if you are free. Otherwise, we'll not do it tomorrow. But uh, the next class we'll do is we'll start doing the curves like parabola and ellipse, especially we need to do, because those are simple curves. You need to understand what is happening. So we'll do this, maybe like one or two more classes should be sufficient, and then we'll go to AMC papers and stuff, and we'll see questions from there. Okay.
Okay. Yeah.
What is happening right now? Your dad was saying that there is some test and all that is happening 17th or something.
Oh, yeah, it's Holbrook. I mean, Joe Holbrook, JHMMC. It's not. I mean, I took it last year too. It's literally just for practice. The syllabus is not too different from AMC 10, except that the level is a bit less. But I think you can get by with practicing questions. That's what I actually have started doing. I started like this week practicing questions. So yeah.
Okay. AMC 10 date is when? When is the date for the exam?
November 10th, so like a month.
Okay. Okay, then we need to do more. So parabola, ellipse and all, has it ever come in AMC?
Not really. If a parabola ellipse has never come, that's for sure. If parabola does come, it's in algebraic form, so it's like pure algebra or something like that.
Okay, so we'll briefly look at, we'll probably not look at ellipse so much right now. We'll look at parabola because the equations for parabola are like a quadratic and it might come. This is the general equation of the parabola.
Yeah.
So we will see that, and after that we'll just go to problems. So tomorrow or next week's class we'll do this, and after that just discuss problems for the exam. Okay.
Yeah.
Okay, that's all for now. I'll see you.
Okay.
Bye.
Bye.